So last but not least, I'd also like to introduce the next speaker of this session, which is our moderator. So in my lecture, I've told you how I want to make individual components of a solar cell, but still you need to assemble the whole thing. And Sana is actually going to present you how you can use inkjet printing to very sustainably not just assemble solar cells, but all kinds of electronic devices such as batteries or fuel cells. Sana?
Thank you so much, Adrian. Okay, good afternoon again, everyone. So it's a great pleasure to be here. I'm Sanaz, a PhD researcher from Aalto University in Finland, and my research topic focuses on fuel cells and hydrogen energy conversion. Let's take a journey today in order to investigate the challenging framework of sustainability within the area of renewable energy technologies. We are all aware of the urgency of green transition, but let's pause for a moment and look at the broader picture. When we delved into the fabrication techniques for these renewable energy technologies, question arises. How green are our fabrication methods for these renewable energy technologies? What environmental footprints do we leave in the process? And as we tread the green transition path, should we reassess the steps that we take in? Sure, we are always talking about the unlimited potential of solar cells and wind power, but do we also have unlimited material resources in order to provide the necessary energy conversion devices for these technologies? These questions will kind of guide us through today's presentation. Yes. So now I want to bring a mature fabrication technique to light, which I'm sure that all of you are familiar with, which is inkjet printing. So inkjet printing digitally deposits the ink material on the substrate in a layer-by-layer fashion, which provides thin films with multi-material components, and without the necessity of using physical content or using the masks, which makes our life much easier. It also is very cost efficient, very fast, and provides precise patterns, which leads us to tailoring the microstructure. And when it comes to the electrochemical devices, tailored microstructures becomes really important. And moreover, it almost has zero waste. Now I want to draw your attention to using this fabrication technique to creating solid oxide fuel cells. These devices are designed for high efficiency performance, and they provide noiseless performance. They are also fuel flexible, which means that you can also use other hydrocarbon fuels instead of hydrogen to produce electricity. They have high efficiency, and they also provide a potentially long lifetime. But despite their promises, as you can see, there is a limitation, because they are operating in a high temperature, around 700 to 1,000 degrees, they are suffering from severe degradation. So one way to reduce the operating temperature without compromising the performance is to create some high performance material for the electrodes with tailored microstructures in order to provide a high performance solid oxide fuel cell that works in lower temperatures. And we can use inkjet printing for that purpose, because inkjet printing can tailor the microstructures, especially for the cathode electrodes, as they are the leaders of somehow they drive the activation loss for the solid oxide fuel cells. In order to do that, first we need to develop the inks. For developing the inks, first we are coming with the ink formulation, which is the core part of our research. In my PhD studies, I developed 3 different inks in an organic medium, which are LSCF, a conventional material for solid oxide fuel cells, and also copper iron oxide, which is a spinel material, and the inkjet printing ink is developed for the first time. In order to, and this is challenging because the inkjet printing, the ink that you're providing for the inkjet printing needs to be jettable and functional at the same time. In order to make sure that our ink is printable, we need to measure some ink properties like particle size distribution, viscosity, surface tension, and density, and calculate the Ahnesorge number here, which, yes, here, and make sure that ink is lying in this green area. Let's delve into the fascinating relationship between the microstructure and also the electrochemical performance. So here at the left column, we have the inkjet printed cell with only 0.03 grams, and you can see the favorable spread of the active material here. And in the higher magnification SEM image, you can see the conjugated nanostructured morphology. Unlike the dropcast one, which is evidently has more material deposited, but it also has a poor distribution of the active material. And this microstructure is also reflected on the electrochemical performance, as you can see it here. The ohmic resistance is more than 3 times lower, and also the R3, which is a representative of mass transfer resistance, which is also highly dependent on the microstructure, is more than 5 times lower than that of dropcast one. Now let's go for my last ink, which is copper iron oxide, which is, as I mentioned, developed for the first time. In the left column, you can also see the same behavior in the LSCF ink, the kind of the nanostructured morphology, a homogeneous coverage on the surface area. And also here we have a higher magnification SEM image that shows that inkjet printing is able to break the particles during the inkjetting process and providing a higher specific surface area during the fabrication process, which is a huge advantage for electrochemical devices. And this is also the interface area analysis of our cells. As you can see, this is the interface between the electrode and also the electrolyte. And inkjet printing provides a provides a better interfacial area, as it has a high velocity and it penetrates deeply on a porous substrate, which is also beneficial for our performance. And this is also the electrochemical results of our cells. As you can see here, our inkjet printed cell provided more than several times more power density compared to that of dropcast cell. And here goes to the final slide. As you can see that we were only depositing a few grams of material, but our performance was kind of 7 times better than that of the drop casting, which makes the microstructure really important in the fabrication technique. Also, we do not have any waste when we are using inkjet printing. Moreover, we have diverse applications for this fabrication technique, because it can, for example, for the textile engineering, as this fabrication technique is able to penetrate into the texture. And now these are our published papers, and this is the this is the video, which hopefully will be played, of our inks. So yes, thank you. Apparently it's not playing here, which is a pity, but consider that something is jetting from the nozzles.